Welcome to breadboarding. In this video 7 of the Nanocomp breadboard video controller series, we're going to be carrying out step 5 in our plan, which is to upgrade the video RAM to two 32K single port chips to replace the one dual port 4K chip. In some of the more recent videos, there have been a few issues with sound levels after I had to reinstall Windows on the main laptop I use for doing this. Hopefully, following some feedback from a couple of viewers, the audio levels should be much better in this one. So please let me know if everything's okay, and feel free to make comments. I generally try and get a response back within a day or two. So this is our plan. So step 5, which is we're on now, is replacing the previous dual port RAM we just talked about with these faster 32K chips. What this will allow us to do in some of the later numbers down here is to start to use that larger RAM to be able to do 2-color graphics, and eventually to be able to do 256 color palette out of 262,000 colors. So that's much closer to the original VGA spec. So this is a chip layout of the 32K RAMs that we're using. They're actually called 71256s, and they're a little unusual in that although they're 28-pin layouts, they're actually on a 0.3-inch pitch, so they're quite narrow and very long. Although the pin identifiers are very similar to the EPROM chips and other larger RAM chips, so the way how the pins and the address lines are laid out is very, very similar. Now these are quite fast. They're 15 nanosecond access time versus the larger chips that we've used for the main RAM, which are 128K and even larger 512K chips. Those are typically about 55 nanoseconds. Now this compares very favourably though with the memory chips from around the late 70s and early 80s, which quite often had an access time of 450 nanoseconds. They're quite a bit slower, and some of the design constraints of using that slower RAM did force the designers of video cards in that time to have to make some compromises. Because this RAM is so fast, it will allow us to be a bit more flexible with the design in some of the later videos with doing high resolution graphics. So you're going to be using a total of 64K, but in this particular step we're only going to be using two 8K blocks of that RAM because we don't actually need the full RAM to start with. And we've got one 8K block for the characters, just like before, and we're going to know that as video RAM number 1. And then we're adding an additional RAM chip here for the colors, and that gives us 4 bits for foreground and 4 bits for background, and we'll call that video RAM chip number 2. Now, because this RAM is not dual port, so we don't have 2 lots of address and data pins on each side, what we need to then do is to add support for accessing the data bus from both the CRTC and the CPU. So we need 2 bidirectional buffers. We also need to be able to multiplex the CRTC address signals with the CPU signals. Now, in an earlier version of this, I did use multiplexer chips. However, the multiplexer chips pin out on breadboards is quite awkward, and what I've ended up doing is using tri-state buffers which have all the inputs on one side and the outputs on the other, and that makes a much cleaner design on the breadboards. And then finally we've got a couple of D latches that we're using to hold the value of the RAM whilst the CRTC is accessing it, so that if the CPU needs to come in and make modifications to the RAM, then the value that's being used by the video display at that point in time won't be changing whilst we're accessing it using the CPU. One thing we also need to make a note of is that CRTC only does memory address 0 to 13, so that's a 16K region. Now that's fine for what we're doing here because we only need to access 8K at a time for the characters, and I'll explain that in a minute. And in step number 5, what we're actually going to be doing is taking the 2 8K blocks of RAM and mapping that into the 16K address area from 8000 to BFFF, which uses the address decoder 0 line. So that's the signal that we're going to be using for selecting the video RAM. Now, the way how we're going to be laying out the video RAM is we want to be able to access the byte for the color for a particular character at an even byte, and then we're going to access the character value at odd bytes. And what this means then is that the two RAM chips are going to be interlaced between A0 being 0 and A0 being 1, so that we can access the character and the color values sort of sequentially. And this makes it easier to program, and is the way how the VGA cards originally did this. So we've got 4 bits for the foreground. So this is the high nibble, a nibble being a 4 bits or a hexadecimal character 0 to F, and 4 bits for the background, that's the low nibble. So we'll know these just as F0 to F3 and B0 to B3, and those are going to be red, green, blue and intensity. So F3 is red and B0 will be background intensity, for example. And then if we wanted to say have a white foreground and blue background, as we did in the earlier videos where we are hard coding the colors just by wiring the pins to particular values, then that would be hexadecimal F3. So our characters are going to be odd bytes, so where the A0 address line from the CPU is 1, and that will allow us to have up to 256 characters. Both of the video RAMs are going to be enabled when the CRTC chip is accessing the RAM, because we're going to be accessing the character and the color in parallel. But only one of the VRAMs will be enabled when the CPU is accessing the RAM, and that's going to be determined by the address 0 signal. And as we said previously, the latches hold the VRAM contents while the CPU accesses the RAM. And depending on how this works out, we might need to do future changes to the CPU memory timing so that the CPU may delay accessing the memory to allow for the CRTC to finish reading the memory. So it depends on how much interference we get when we've got heavy access to the video memory from the CPU, but we may expect to need to do something with the timing there in future videos to address any interference that we might have. Okay, so let's have a look at the block diagram we had left over from the previous video. So I updated the block diagram to consolidate everything into the video PLD, and I've called this video PLD1 for the moment because you may add some more PLDs at a future point in time. And basically this just consolidated 6 counters, logic chips and various other flip-flops and things into a single PLD and simplified things quite a bit. And we can see here that at the moment with the previous video we had one dual port 4K chip for the video RAM. Now that would allow us to do up to 30 lines or more of 80 characters, but there isn't enough RAM in 4K to be able to do 30 lines of 80 characters and include the colors as well. You could do 25 lines, but I really wanted to try and use the full 480 pixels for each screen, which means we need to use 30 lines. So now let's look at the revised design. So what I've done here is I've moved some of the areas that haven't changed between the previous video and this one over to the right here, just so we've got a bit more space. I've also renamed this character generator RAM. So this stores the bitmap pixel of the characters, so the raster image of the characters, just to distinguish that from the character and color RAM that we're talking about now. So we'll be adding our video RAM chip number 1, which is the character values. So that's very much like we had in the previous video, apart from it's a bit bigger. And then we've got the second chip here, video RAM number 2, which is providing the foreground and background colors for each character cell. Then to support that, what we need to do is to be able to multiplex the CRTC address signals and the CPU address signals to the single lot of address inputs on the video RAM. Now, originally, as I said, I tried doing this with some 4x2 multiplexers. So this has 2 inputs for each output, and you can toggle between the two with an input value. The problem with those chips is that the pin layouts weren't very good for putting things on breadboards, and because they were scattered around each side of the chip, it meant a very, very messy layout. So what I've gone for is these 4 octal buffers. So we use 2 buffers to do the CPU addresses and 2 buffers to do the CRTC addresses, and then we'll toggle between the two on the basis of the Y0 signal. Generally, when the Y0 is 0, the CPU will be accessing the data and the address, and when Y0 equals 1, it will be the CRTC. Now, an important aspect about this, as we've already said, is that because we want to be able to access the color and the character as sequential bytes, so the color being 0 or even bytes and the character being odd bytes, then what we're actually doing is we're only using the CA1 to CA13 in this multiplexer here, and we're actually going to be using the lowest bit in the address line, the 0 and the 1, to toggle between which of the RAM chips is enabled. So effectively the lowest bit on the CPU address bus is being used to toggle the chip select for each of the video RAMs there. So then the output from the color RAM is then stored in a DTAP latch at a particular point in time in the cycle, and that provides 4 bits for the foreground color and 4 bits for the background color, and that just goes into the existing multiplexer chip that we've got, where we've just been hard coding the values for the foreground and background color in previous videos. So this now allows us to specify up to 16 colors for the foreground and the background for each character cell. Then we've got another latch for providing the character address for the character generator RAM. So the bottom 4 address bits of the character RAM are driven by the row address outputs from the CRTC. So this provides a line from 0 to 15, which drives the row of the character, and then the value for A4 to A11 for the character generator RAM provides the actual character value, and we've got 256 characters there. And because this is dual port RAM, then we can freely update the character generator RAM at any time we want to from the CPU. And then this just goes off to the shift register as was done before. And finally, to allow the CPU to be able to access the video RAM, we then need to include 2 bidirectional buffers. So this allows the CPU data bus to read and write to the video RAM. And again, the chip enable signals on these video RAM chips is such that the CPU can access each of these RAMs alternately as we cycle through the address range there. So now let's have a look at the KiCad diagrams. I've got the previous KiCad diagram in the PDF, and we can see here that this is the shift register down here, and what we're going to do is to move the shift register from here up to here, so to make things a little bit neater. And this dual port RAM, which is used currently for the character values, is going to be removed and replaced by a lot more chips. So we're going to need to fit up to about another 10 or 11 chips here, I think it is. So here is the overall view of the updated schematic, and what we'll do is we'll just zoom into this a little bit to explain what's going on. You can see here in the chip select logic, we're taking the A0 line and the Y0 address select for the video RAM, and then we're inverting those values, and we're using combinations of the inverted Y0 and inverted A0 and the original values to drive the various chip enable signals, and we're just using an AND gate with an inverter on it to make it into an AND, just because we need to use inverters elsewhere, so that just makes it a bit easier. We might replace these with a PLD, but I've run out of PLDs at the moment. I've got some on order. They might arrive in the next week or so, in which case I might swap those out with the PLD. So then if we look at the board at the top here, we can see that we've moved our shift register up here, so it's moved from down the bottom up to here. And what I've also done to make a bit more space, I've moved the multiplexer over to the left here. So this is the foreground background color selector, and now this is being wired into the output of the color latch, which is coming from the video RAM, and so this is now wired up to the foreground, background, red, green, blue and intensity signals. And for these, what I have done is I've turned them upside down, and I have actually ended up mapping the 0 to 7 and the 7 to 0, just to make the wiring out of these easier. So this should mean we can have straight wires between the bidirectional data buffer here. So this side is going to be connected to the CPU data bus, and then this side can just have straight wires going across here. So we'll make the wiring up of this much easier. If we tried to keep with the D7 going to CL7, then we'd have to have crossover cables and things here. And what I might do is, when I do the chip labels for these, what I might just do is to relabel these so that they start at D0 down to D7 rather than the default chip way. It doesn't really matter from the use of the chip, it just means it's less likely that going to make mistakes when trying to wire things up. So that's the way how the color output has changed, and what we've got down here is a color RAM. And what I can also show you here, these are the 2 buffers which are being used for the CRTC address bus. So we've got the two buffers here which are taking the MA0 to MA12 lines, and then effectively the address 13 and 14 lines at the moment are just hardwired to 0 for the moment. When we come up to do the graphics, we're going to get a page register to allow us to switch between different banks of RAM in the CPU address space, but for the moment we're just going to stick those at 0. And then we've got a second buffer here which allows us to hook in the character RAM to the CPU data bus, and there's also then a latch here for reading the values out of the character RAM and then feeding those latched character address values into our character generator RAM over here, and that's very similar to what we did before with the previous video RAM. And we've got our CPU address signals coming in down here, and we can see here as well that we're also multiplexing the read-write signal from the CPU, whereas the same signal which is going to the video read-write is hard-coded to high here. So this is one value of 1 or 5 volts, and that basically means that when the CRTC is accessing the video RAM, it's always reading it, it's never writing it, so we don't need to have anything else there. Now this layout is substantially simpler. I might just show you the layout that I did originally with the multiplexer, and it's quite a bit more complicated. So this is the multiplexer version, and just to give you a quick indication, you'll see down here that the signals are way more complicated. We've got a lot of buses being replicated all over the place, so we've got signals coming from all over sides of the board. So this was getting really complicated using these multiplexer chips, so that's the reason why I switched over to use this way. It's still fairly complicated, but it's much simpler. We've only got the address bus and the CRTC bus coming down one place, and we don't need it going all over the place. So I thought it was worthwhile redoing this. It's why it's taken me a little bit longer to do this, because I've done all the diagram using multiplexer chips and I had to redo it using these buffers just to simplify it. And just to give you an idea, if you look at the chips here, you can see here that these 541 chips have the inputs and outputs lined up opposite each other, so it makes it very easy just to plug in bus signals along here and come out the other side. And if you look at the multiplexer chip, the 157 multiplexer chip, you can see that this has got the 2 inputs and the output, 2 inputs and output, 2 inputs and output. So it means you've got to have all the bus signals coming in all over the place, so it gets really, really messy very, very quickly. So this should result in a much simpler layout on the boards. So what I'm going to do now is just show how I worked out how to document which of these signals needed to go into which pin, because it was getting quite confusing. So what I've done here is a spreadsheet where for the video RAM, for the color and the character RAM, for the character generator RAM, I've basically identified the number of signals. I've actually put a C in front of the address signals for the CPU address bus, just so that I didn't get confused when talking about A1 and A2 and things. So what this shows is for the video RAM 1 has got address A0 all up to A14. So with 0 indexing, that means that it's got 15 input pins, and that gives a 32K address range. But the top 2 pins we're just going to be hardwiring to 0 for the moment, because we're only going to be using the bottom 8K for the moment. So that's the reason why we're only using C1 down to C13. Now you'll also notice we're not starting at 0, we're starting at 1 and we're going to 13, whereas the CRTC address output is going from 0 up to 12. And the reason why we're doing that is because we're using the CPU address 0 as part of the chip select between the 2 chips. And so you can see here we've got the chip enable for video RAM 1 and the chip enable for video RAM 2 are making use of the CPU address signal in both of those. And then the output from this, so we've got video 1 data output. When it's talking to the CPU, it's just going to D0 to D7, and that's through the buffer. And when it's being used by the CRTC, I've got the character latch address A4 to A11. So that basically means that the output of the character RAM here is providing the top 8 address bits for the character generator RAM. So the bottom 4 address bits are being provided by the CRTC row address 0 to 3, and then the character latch address is providing the next 8 address lines. Then we look at the video RAM for the color, and we'll see that I've just called this V2A0, and in fact on the schematics, because these two lots of signals can be joined together because they're the same, then in fact the V1A0 and V2A0 are the same, and so they can be wired together, and again that makes things a bit simpler. Similar to this one, we've got CA1 to CA13 using CA0 for the chip enable, and we've got MA0 from the CRTC to MA12, and again we've hard coding the A13 and A14 address lines to 0, so we're only using 8K. Now the output for the data for the color RAM, D0 to D7 goes off to the CPU when it needs to be accessed, but then we're using color latch 0 to color latch 7 to latch the output of the colors, and then the color latch is then being fed into the multiplexer for the foreground background colors. The character generated data output there is accessed directly by the CPU data bus, and it's dual port, so we don't have to worry too much about that. And then the output from a CRTC point of view goes to the shift register A to H inputs. So that shift register takes a row of bits for a current line of the character and then serialize them into ones and zeros for the video signal. So that's the way how I worked out how to do the pin decoding. And finally, the CA0 and Y0 signals are being used to do the chip enables, and all I did here is a simple sort of truth table to work out what values I was wanting for the character chip enable and the color chip enable under what the different scenarios where I wanted the chip to be enabled, when it was 0 and when I wanted it to be disabled. And I was able to work out from that in fact the logic for that is quite a bit simpler than I'd previously thought. So the logic for that is fairly straightforward. We've only seen that in the schematic, where we've basically got a couple of inverter signals for the address and the Y0 lines, and then we've got some AND gates and things to provide the necessary signal. So that's the way how we worked out everything. So what we're going to do now is to have a look at the board, and we're going to add some additional breadboards to the layout, and then start to remove some of the existing chips and to move the shift register up the board into the higher area near the rest of the PLD and the CRTC chip. Okay, so this is the current state of the board, and what I'm just going to do first of all, before I add, I'm going to add some more board down the bottom down here. What we're going to do is to move the shift register here over to here, and we're also going to move the foreground background multiplexer from here over to here, and then there'll be some more things adding in here. So what I'm going to do is I'm just going to record that without any audio, and we'll speed it up. So I've moved the shift register from down here up to here, and I've rewired and tidied up these cables in here, and all the various control signals are now connected up to here. And I've gone through and I have checked off all of my connections and things, made sure everything's connected to the right place. So that little bit is done, and now the next thing we're going to do is to move the multiplexer from here over to here, and we'll rewire it, various signals and things here. So here are the chips we're going to be using. So these are the 32K fast RAM chips, and you can see they are 28 pins but only 0.3 inches wide, so they're quite long and thin. So these are the RAMs that we'll be using. These are two 574 latches, and what I have done here is I've got custom labels on them. So this one has got the color latch 0 to 7 and the various background intensity, background blue, background green, etc. And then this other one here has got the video data 0 to 7 and the A4 to A11 to go to the character generator RAM. And then over here we've just got the 745 buffers, a NAND gate and a inverters, so we can do some of the chip enable logic. And then over here I've got 4 74LS541s, and these are in fact got the labels reversed, so they start at 7 at the top and go down to 0, whereas I think the default labels are the other way around. So it just means that when we're wiring things up, these are going to suit the way how the chips are orientated in the layout and make it a bit easier and less likely to make mistakes. So now we've done all the design and we've updated the original part of the board to move some of the chips around to give us a bit more space. What I thought I'd do is I'll break the video now, as it's got up to about 29 minutes I think, and we'll have a part 2 where we'll start to wire up the new parts of the board, and who knows, by the time we get around to testing this we may even need to go on to a part 3. So if you don't want to miss out on the next video, please hit subscribe. There will be a link on this current video once the next one is published. Please hit like if you found it interesting, and thank you for watching.